doesn't impact on the mutation that occur before that selection is applied. That's a very important result. So I'm going to go quickly through the next 2 or 3 slides. The main point here is that the mutation rate is very low, but we have numbers on these rates in different systems. It can vary from 1 to 100-fold in a single organism, depending on many parameters, depending on the sequence, depending on the location of the chromosome, depending on the cell type, number of parameters that impact on the mutation rate. In prokaryotic system, it centers around 1 in a million base pairs per cell division. And in eukaryotic systems, generally speaking, the mutation rate is about 10-fold higher. Never mind the exact numbers per locus, per system. These are all very interesting tables for our information. They're fun to look at, but that's generally what I just said is the norm. So what we're going to look at today is the potential impact of mutations generally on the phenotype, that is on gene expression. We're going to then talk about spontaneous sources of mutations. We're going to then discuss the notion that one can perform mutagenesis using mutagens. These are compounds that greatly increase the natural mutation rates to over 1,000-fold. These compounds are often used in genetics to obtain interesting mutations with interesting phenotypes. If one wants to use mutations as a tool to investigate gene function, remember last time I insisted on that notion. And finally, we're going to end with a discussion of DNA repair pathways. So when mutations arise in the genome, there are a number of different pathways that, first of all, sense the defect or the damage, and specific pathways will be induced by specific types of damage, and these pathways are induced and lead to the repair of the damage. So we're going to discuss that a little bit. And these mechanisms have evolved in that they greatly increase the fitness of the cell and therefore the organism that possess these repair pathways. Okay, so first subject, what is the consequence of mutation? And so the one thing to keep in mind here in this subtopic is that in fact mutations arising randomly in the genome, they can affect pretty much any gene expression element that we've discussed so far. They can affect promoters, they can affect splice signals, they can affect the polyA site, and of course, they can also affect the coding sequence. Oftentimes, we tend to focus perhaps a little too much on the coding sequence, a little bit too much, because I'd like to remind you that very little, a very small fraction of our genome actually contains coding sequences. It's way less than 3% of the whole genome that actually is mutated in a way that reflects the coding sequence. So, in fact, mutations tend to perhaps have an impact on gene expression signals that sometimes do not, in fact, change the coding sequence, but still affect gene expression. So we're going to discuss all these issues. And so now, what you have on that table makes that point very clearly. On top, you have the type of mutations that affect the coding sequence, and on the bottom, a subset of the types of mutations. This is not an exhaustive list that are so-called regulatory mutations, and as I just said, they affect gene expression. So in the coding sequence mutations, I'm going to show you examples in the next slide. Some are affected very much silent, and so simply there's a nucleotide change that doesn't change the amino acid at that position because the code is degenerate. We still talk about the mutation though. It's a change from wild type. It's just the protein is a change. So of course these don't have any effect on the phenotype. So then importantly though, now we have three other types. Missense mutations, which change a codon for another, and that of course will change an amino acid in the predicted polypeptide. We have nonsense mutations, which creates a subcodon and prematurely terminate translation, so that generates a truncation in the protein. Whether it occurs early or later can have different effects. And we have frameshift mutations, which result in wrong sequence of amino acids. And what that means is the addition or deletion of a number of nucleotide that is not a multiple of 3. We'll talk about this in a slide to come. If you add a multiple of 3 nucleotides, 3, 6, 9, 300, 600, or you delete such sequences, this is not a frameshift mutation because you are removing or adding a fixed number of codons. So in fact, you talk about of these changes as in-frame deletions or in-frame additions. We'll look at this in a few minutes. Now, regulatory mutations is anything but these type of sequences. Mutations in promoter changing, in fact, in general, in more general sense, the activity of the promoter. So you can, for example, mutate PATA box, that probably would tend to reduce the activity of the promoter, and or you could mutate, for example, an enhancer far away from the promoter, and that limits the strength of transcription from that promoter. You should know that it's also possible to mutate enhancers or promoters, though those mutations are more rare, in a way that you increase transcription. That's also seen. Okay, so these type of mutations are not necessarily what you call loss of function mutations. They can also be activated mutations. And so you can mutate life sites. We'll discuss that. That's important. And I cannot say this in just a couple of words. And polyadenylation sequences, and to be continued, any kind of element that we may not necessarily understand yet. There's also another kind of mutations which can affect, for example, microRNAs, which we're going to talk about later in the course, which in fact affect RNAs that in fact impact on the expression of another gene. So that can be an indirect effect of the mutation. So really, don't think this is a full listing here. We just want to make the point that mutations can affect coding sequence or gene expression elements. So now we can talk a little bit about just simple coding sequence mutations. As I defined them before, silent, so that's the wild type sequence. The silent mutation, as I said, doesn't change the amino acid. This is a missense mutation, changing an amino acid, and a nonsense mutation introducing a stop. Two thoughts. First, the missense type mutation is going to be much more frequent than the stop, because the stop requires a very specific change of specific codons in order to transform them into a stop codon. The second thought is that these mutations may have vastly different consequences depending on where they are in the protein and what's the change. So you could have, for example, this leucine mutated into an alanine or isoleucine. Well, that may not be such a debilitating mutation of the protein, so you may see no phenotype to a mild phenotype, for example. But if you change the leucine to an aspartate, you're introducing a charge, and that's going to be a mutation that has a grave consequence on the protein. And so, genetically speaking, all missenses are not alike. And same thing for nonsense mutations. You may well imagine if you have a nonsense mutation, maybe that truncates the last 5 amino acids, that might not be as deleterious as a nonsense mutation in the first half of the protein, truncating the rest. And so now we're going to talk a little bit about frameshift mutations. So here's our sequence again, and you see that when you introduce one single nucleotide in the coding sequence that is not a multiple of 3, you're disrupting the frame. And the importance of this is that it completely disrupts the way the ribosome reads the sequence downstream of that frame shift. And so some amino acids are going to be added that have nothing to do with the normal protein sequence. And in fact, a stop codon is very likely to be encountered downstream of that frame shift. In a sense, the sequence downstream of the frame shift, even if it's a single nucleotide, becomes non-coding. And in non-coding DNA, and there's a calculation for that, that use a probabilistic reasoning, you have 95% chance of encountering a stop codon, one of the 3 stop codons, in the next 30 nucleotides. So you see that frame shift not only adds completely unrelated amino acids to the polypeptide, but also leads to truncation. Same thing holds for deletion. And as I said, if you insert or delete, say, 3 nucleotide of multiple within this coding sequence, then you have in-frame deletions or insertions. And so that's a very different situation. So this is, for example, just to look at this peptide, you have, for example, if you remove 6 nucleotides, for example, no matter where they are in the codon, it doesn't matter. You have, for example, U, trip, cis, etc. You're removing phenylalanine and arginine, for example. But the peptide is still translated to the end. And the residues that constitute that peptide actually have a relationship with the wild-type peptide. Okay, but that peptide will be missing some residues. And in fact, that has also very severe consequences. Okay, you'll be missing some residues, but you'll be making a related polypeptide to the one that's nominated. I'll talk about this when we discuss splice site mutations. So this has a relationship with splicing. And that's going to be a very important point. So keep this issue of the reading frame in mind for a few minutes. Promoter mutations. I sort of set up, gave you the main of that story. You can have up or down mutations. I think it's fair to say that the great majority of promoter mutations are, say, loss of function mutations, or disrupting the activity of the promoter. You'll get a lower transcription level and less mRNA made per unit of time, and that will lead to a depletion of the protein. And this also includes, by the way, it doesn't only include the Tata box or the cat box, but also enhancer elements that may influence transcription of the basal promoter. Splice mutations now, you see, look, you can look at this in this, the bottom part of this slide. And here's the first point. So we're looking, for example, here at the donor site, right? So we have an exon intron junction that would be the donor site. And here's an important point, actually, is that, again, mutations have different severities in that case as well. So, you may have mutations that completely inactivate the splice junction. Same is true for the acceptor site. But some mutations actually reduce the activity of that splice acceptor site, for example, splice donor site in this case. And so again, we may actually, with different mutations, reduce gene activity by 20%, 40%, or 80%, depending on the effect of that mutation on that splice. It's not always all or none. So here's a very important point, so important that I actually imported a figure from somewhere else. Not even. This tell you how important this is. Because I felt that, the chapter didn't do a very good job in explaining this. And so let's consider splicing of a simple locus here. Look at the top here. So we have donor, acceptor, donor, acceptor, donor, acceptor. And so they pair, as you know, so we don't have the branch sites. You know about the branching and lariat and all that. We don't show that. So we are splicing together this gray exon, the light green exon, the dark green exon, and the black exon. That's what you see, say, normally in a situation. I know, and I know that you know, that splicing is a lot more complicated than this. It's not that simple. It's not like those introns are spliced out neatly, one after the other in sequence. We know that that's not that simple. But let's consider just a simple situation to explain something about mutations and how splice junctions can be affected. So let's consider first a mutation in the acceptor site. Let's say this one here. So I put a little star here on this acceptor site. And so what would happen then in that case? And let's say again, that we're completely removing the activity of this acceptor site. So splicing of the other exons upstream are not going to be affected. So this is still okay. We're still splicing these together. And then this donor side kind of pair with the normal acceptor side. And what's going to happen? It's going to pair with another one that is available to that splice donor side. And so look at what happens. It can pair with this one, for example, the next one downstream. And splicing is going to go happen just the same. We have a branch site over here, and we're going to splice then the light green exon with the black exon. And what's the consequence of that? The exon that's normally included, the dark green exon, is actually not seen as such and is actually not included in the mature mRNA. We're leaving out an exon. And the mature mRNA then has an aberrant exon to exon junction, which normally doesn't happen as a result of this mutation between the light green and the black exon. See that? And so now let's think of a mutation in the donor site. What happens there? So let's just imagine this donor site there is mutated, and then you have a very different story. So again, we have upstream splicing occurring normally, so this is fine, that junction is okay. And the machinery is just not going to see this donor site. And what's going to happen is it's going to see the next one, and this is going to pair with an available acceptor site downstream. And so in other words, that's the normal splice junction that's created, but we have, or the machinery has completely missed altogether an intron that should normally have been excised. As a result, you see the mature mRNA with an intron. So what's the consequence of that? Well, let's first talk about the second situation. What happens if a mature mRNA has an intron in it, as is shown here, for example? Well, we know that introns are not coded sequences. So the same logic applies. The ribosome is just going to happily translate through these two exons, and it's going to come here, and it's going to keep translating, and these are going to be completely unrelated amino acids. We're going to have a few residues added, and then stop codon. That's the 95% chance in 30 nucleotides. Okay, so we're going to have a truncated product with a few residues depending on the intron sequence and the stop. More interesting, I think, is the second case. What happens if we're missing an intron and we're creating an aberrant exon-exon junction? Well, we have all the elements to understand what happens here. And so what happens to the translation product, and what is the critical parameter? And this is where we are confronted with this issue of the reading frame. So let's think of the ribosome. It's going to come here, translate the two exons here as it should, that's normal sequence, and then the ribosome is going to keep translating here. Now, these black codons, right, of the black exon here, they're present in the normal mature mRNA. Okay, so in reality, is this just removing a specific number of nucleotide residues that are part of the dark green exon here? It's just not there. Does that have a consequence of the translation product? And what's the critical parameter? Anybody wants to venture a guess? Yes.
What do you mean by parameter?
I mean, what is the physical element on that locus that's going to impact on the answer? Is this going to be just an in-frame deletion? We're just removing the dark green exon. So does that just mean we're just translating the light green and the black exon and just fused together? Do you have an answer there?
Would it mean loss of function or partial loss of function?
Okay, but what's the effect on the translation product? In other words, why? Yeah.
An in-frame deletion because it's a multiple of 3.
And what's a multiple of 3?
The exon that's being removed, or the number of nucleotides in that exon.
Okay, the number of nucleotides of the exon that's removed is a multiple of 3, and therefore that's an in-frame deletion. Well, you only have part of the answer, because in fact, your answer to your own question, that's the critical parameter, is the number of nucleotides that are constituting the dark green exon that's missing. And so, and I didn't tell you that, but the answer is, if the dark green exon that's apparently removed is actually a multiple of 3, let's say, for example, 900 nucleotides, you're going to be missing exactly 900 divided by 3, 300 amino acids, and you're going to have an in-frame deletion. But that junction is actually going to be in-frame because you've removed, if this exon is a multiple of 3, a set number of codons, or an even number of codons. But if it is not a multiple of 3, if this exon here is not here, sorry, this one, if that's not a multiple of 3, then that junction will not be in frame. Therefore, as the ribosome starts reading the black exon that's been fused, it's going to encounter a frame shift, and then it's the same story. We're going to have aberrant residues or amino acids added, and then a quick stop codon to finish that translation. Is that clear? So the important parameter here is whether it's the number of nucleotides of the exon that's spliced out, and whether it's a multiple of 3 or not. Yeah?
You mentioned that there is a 95% chance to meet stop codon after 30 codons.
Okay, 30 nucleotides.
Nucleus.
Yes.
Does this mean that 30 divided by 3, which will give us 10?
10s on average, yes, sometimes more.
So there is a 95%
Yeah.
Of the proteins which have a 10, a chain of 10 amino acids.
For a single mRNA, that number is the same. That is, that fusion is going to be exactly the same. So for this particular locus, you will always end the translation in the same way.
I mean, is there 95% of proteins that are 10 succession of amino acids? Based on the calculation, 95%.
No, because I'm not sure I understand the question. Let me try to repeat. Does that mean in 95% of the genes that have a coding sequence, does that mean that they end translation prematurely? Is that a question? Answer is no, because in fact there is a coding sequence that provides a reading frame for the ribosome. So this argument is only if there's a frame shift, or if there's a splice mutation, as I just explained. So it's an invariant situation. Does that answer the question? Okay.
I'm just wondering, shouldn't we actually consider the light green exon to be like a multiple of 3? Because if it's not, then it's going to be a frame shift. It will pick up the next nucleotide of the black exon.
So the question is an important parameter the number of nucleotides in the light green exon? And the answer is I don't think so. I think that the important parameter is actually the reading frame, first of all, and that's actually defined by the starting AUG, which is in that exon or an exon string of it, we don't know, but I don't think that's a parameter. Given you have a reading frame, the essential parameter is the number of nucleotide in the exon that's missing. Okay. Something else about splice junctions. I guess even better. So you know that splice junctions, donor and acceptor sites, they're really not defined that well at the nucleotide level. I mean, it's not like you have very strong consensus sequence. I mean, you have AGGC, for example, as a 3' splice site. So that's the acceptor site. So that's an intron here in dark color and an exon. And in fact, that's fairly, I'm not going to say easy, but it's not too uncommon for mutations to create a splice site somewhere where there naturally isn't one. Okay, it doesn't require much changes. For example, a single nucleotide change can in fact create another splice site. So in that case, for example, you're creating an acceptor site that's farther into the intron, and you are adding sequences to the exon. So you're creating a new fusion in this between exon 1 and exon 2. And so then the parameter, if that frame is kept, depends on the number of nucleotides over here. Do you keep the reading frame, and do you go into exon 2? In that case, it's an in-frame insertion. If the reading frame is not kept, again, you're going to repeat the subcodon pretty soon. So splice site can actually also be created and generate variant splice junctions. And that's an example for the 3' splice site. That's also, the logic is also true for donor splice sites. You can also create donor splice sites by mutation. So I hope I convinced you that there's a lot more to mutations than just changing an amino acid and changing the effect of the protein. Now, mutations can revert. So, and they can revert naturally, or they can be revert through the action of mutagen. So you can have a starting mutation and throw mutagen on your yeast, for example, and generate a high number of revertants. So it's not that uncommon. The reversion rate, though, is something like 10-fold to 100-fold lower than the forward mutation rate. But if you look at it on cells or colonies, if you work on yeast bacteria, you definitely will see quite a few of these. Now, reversion, when you think about it, you have a mutation, let's say, for example, this one. So you have a mutation here, and you're thinking of a revertant, say, we're going to recreate the exact sequence as the original sequence was. So that's called true reversion. The nucleotide sequence is back to wild type. The protein sequence is back to wild type, and everything is perfect once again. And that's extremely rare. In fact, I worked for many years on bacteriophage, on E. coli, and then I did also, for better or worse, a PhD in yeast genetics. I've never seen a true in my life. Never. So theoretically, it can happen. Practically, I don't know if anybody's ever seen one. That's probably because other events are more frequent. What else could happen? Well, what else could happen is you could not have a true revertant, but a revertant somewhere else in that gene to compensate for the initial change. So here's an easy way to think about it. For example, if you have a frameshift mutation by adding a nucleotide somewhere in the first half of the gene, that completely kills that gene because the rest of the sequence is good for nothing. Let's say 15 or so nucleotides downstream, you have, what did I say? It said add a nucleotide, the initial mutation, and not remove. So let's start again. If you have a frameshift by adding a nucleotide early in the gene, you can actually revert that just as easily by removing a nucleotide something like 10 base pairs away downstream, because you're recreating the frame, right? Plus one, minus one, we're recreating the frame. And that would be not a true revertant. We're not recreating back the wild type sequence. We are actually compensating for the first mutation with another mutation. In that particular case, it's in the same gene. It's called intragenic reversion, and you get an intragenic reversion. That's also true for missense mutations, actually. You could have, for example, something with a negative charge, aspartate, and you mutate that to something neutral, let's say leucine. So that's a missense mutation that changes the charge of the protein and leads to a strong phenotype. Well, what if you were to change, for example, a glycine neutral to a glutamate, introducing another negative charge? That might essentially allow for protein function, at least some of it, not necessarily back to 100%. They might compensate for the initial mutation. So you have an intragenic reversion event that will allow for the protein to function again, not converting back to wild type. So this is a second compensating mutation elsewhere in the gene. It's intragenic reversions. It's quite rare as well. But it does. That I saw, that I've seen. Now here's another situation, which is in fact why people do gene editing. This is probably a situation that not only is easier to achieve and to obtain, to visualize, but that also tells you something. That's what the genetics and reversions tell you something about the process that you didn't know before. And this is what mutations and reversion events can be important tools in genetics. So this is an example that is very pretty, but that you could just as easily get from yeast, bacteria, flies, worms, zebrafish, a bunch of genetic model systems, and the logic is exactly the same. And so let's say you have a wild type situation where a blue pigment is made in a flower. The mutation leads to a strong reduction in the production of that pigment. And let's say this is a mutation in gene A that prevents the effective transport of that product and leads to decoloration. Well, you could have a mutation in another gene, say B, completely separated from the first one, that in fact leads to an increased transport function. It could be, say, increasing the expression of a minor transport protein, and that's something that's able to transport the pigment, so you go back to wild type. So you mutated another gene is called extragenic reversion, and you get extragenic revertants, and obtaining and isolating extragenic revertants is really super interesting, because let's say you had the gene, the gene for the major pigment transport protein, or doing this strategy can actually tell you, aha, there's another gene that can actually perform that function. It tells you something about the process. It allows you to know more about the function. So you can do this with mutants in DNA replication, mutants in E2F, for example, in flies. E2F in flies, you can do that strategy. It tells you something about the cell cycle, cell growth, and also neurotransmission in worms, has been analyzed that way. So to repeat, this is a very powerful approach to discover genes involved in the process. And to do that, you have to have a starting mutation. So you're using mutation, say, squared. You need starting mutation with a phenotype, and that allows you to get other mutations that revert the phenotype, and then you isolate those genes and you study the process more in depth. Other mutations, not as frequent actually, but they do occur on specific regions of the gene, strand slippage during DNA replication, and these lead to trinucleotide repeat expansions, T and E, trinucleotide repeat expansions. And these are mutations that occur through DNA replication, usually through repeated elements, for example, CG, CG, CG. Note also that C and G can pair. And so, in fact, during DNA replication, that these nucleotides on the daughter strand, that's the strand that's being made, not the template strand on top, the strand that's being made, they can form a stem loop. They can bring back the polymerase a few tens of base pairs, and the polymerase then resumes DNA replication. And what you have done here is you have expanded this region and created additional copies of that repeat. And this can occur, this actually occur more frequently as these repeats are expanded. So up to a certain point, they're stable, and then after a certain number of nucleotides, something like 60 or more, they tend to actually be quite unstable. So these type of events are linked to a number of different diseases. You might have heard of Fragile X. This is upstream of a gene called FMR1. It's not in the coding sequence, and it affects the transcription of that gene, and in addition, creates a fragile site that is a site of the chromosome that breaks easily. So in Fragile X, the normal range of repeats is in that range 6 to 50, and the disease starts to manifest itself over 200 repeats. So there's a range at which, we don't see the disease, but the repeats are perhaps maybe expanding from generation to generation. And other diseases are linked to these phenomena. Again, you want to know more, you do OMIM with that number, and you'll get the link to that disease. You'll get all the molecular biology and medicine about it. Now, how do mutations occur? Mutations can occur spontaneously. They are often fixed by DNA repair systems, as we're going to discuss in a few minutes. So we're going to start that discussion today. They can also not be fixed, in fact, especially mutations that alter the DNA backbone. And they can, if they're not fixed properly, they can lead to gross chromosomal rearrangements, as we're going to talk in the next lecture. And some defects can actually be outright bypassed by specific DNA polymerases. So there are about 20 of them in the mammalian genome and the human genome, and they all have a different Greek letter. There's DNA polymerase kappa, eta, zeta, and others, which are able to switch for DNA polymerase epsilon on the leading strand and go through. But that's really doesn't fix the damage. We're still hitting the same problem, the same spot in the next cell cycle. Okay, now you can, the most common change is a change called a transition, which is a mutation of a pyrimidine for a pyrimidine. So TA to CA is a transition. So those are the most common changes. There are mutagens or occasions where there's a transversion. For example, a GC to a TA, that's a transversion. Those are more rare. So a lot of known ways to induce a mutation in a spontaneous manner is the fact that the pyrimidine bases, namely in the DNA, namely C and T, can, so to speak, tautomerize. They have tautomeric forms in such a way that there is a shift in the number of hydrogen base pairs that these bases can form. And these are, so for example, T, which normally pairs with A with 2 hydrogen bonds, can actually tautomerize and form 3 hydrogen bonds and therefore pair with G. And C, normally forming 3 hydrogen bonds with G, can actually have a tautomer, which pairs with A. And other things can happen to C. We're going to talk about this in a minute. So, these, first of all, these forms are extremely short-lived. They're very short-lived intermediates. Okay, but these do form spontaneously. And during DNA replication, this is a case where, for example, when polymerase hits G, it can incorporate the tautomer of T and place it there instead of C. If T just happens to have that shift at that time, the polymerase doesn't detect that and carries on. Same thing with C incorporated instead of T in front of A. So this slide essentially shows that if I can project it, and yes I can. So for example, here's a case you see where the rare tautomer form of T actually pairs with G, and you see this shift in the electron orbitals of the T nucleotide or base actually makes it able to pair with 3 hydrogen bonds and therefore with G. Same thing with C and A, but C then pairs with 2 hydrogen bonds. So these occur spontaneously, rapidly reverse, but once this happens, T can actually shift back to, the tautomer can actually shift back to A, and then to T, and then we'll have a mismatch. So there is a mechanism called mismatch repair, which normally will actually detect that and fix the problem. Because if the tautomer of T reverts back to the most common form of T in front of G, that's something that doesn't work in the DNA. It's detected as an aberrant structure. The mismatch repair system will come in fact, repair that mismatch. But the mismatch repair system will do that randomly. So it may actually fix 50% of the time. It sees that the mismatch repair system will actually change the T for a C. Great, we're back to the real sequence, the normal sequence, but 50% of the time, it will actually use the T and fix the G instead and put an A. And that is a transition. We have a G for an A that's a transition that's actually going to be fixed in the DNA. Depyrination can also occur. This actually occurs also spontaneously. It's a break in the 1' length of the carbon, and you see that you'll have a excision of a G, and there is a mechanism that's going to fix that. So we have an apyrinic site, and it's called the base excision repair system, and we'll fix that randomly, although it will usually put an A instead. And so if you have depyrination of a G, it can put pretty much anything, but usually puts an A. In that particular case, you have a transition as well. So depyrination of the 1' position, just simply loss of the base. C can do a lot of funky things, as I just told you. C can also deaminate at the 4' position. That creates uracil. And you remember C can be methylated, and deamination of methylcytosine gives you T. So in both cases, you get a transition. Same idea, if you have a mismatch, this is kind of what I just told you, the mismatch repair. If it's not repaired, simply one strand is a template for the daughter strand. You are fixing a mutation in one of the sister chromatids. But if you have a mismatch repair system, again, it's going to fix it to the right sequence, so to speak. Only 50% of the time it does that randomly. So there are a number of compounds that induce greatly the number of mutations that occur in the DNA. These are used by, in fact, geneticists, if they, as I told you, use the mutation as a tool. So if they want to obtain mutations with the desired phenotype, or if they have a starting mutation and want to obtain inversions, they use one of these compounds. So just remember for that table, we have a number of different compounds that can do that. They're used in the lab, and they usually are good to induce great levels of transitions. And we also have things that do frameshift mutations. These are dyes, such as acridine orange, that intercalate in the DNA strands, and how they induce frameshift and actually deletions, we don't really know. It's probably they distort the helix, and that sort of confuses DNA polymerases and leads to loss of a few nucleotides, or in fact big segments sometimes of the DNA, and that can induce frameshift or big deletions. So here, I'm going to give you tools for your information. I don't want you to worry too much about this. I told you already what I wanted you to retain, which is how these things are repaired, and that's exactly the same idea here, which is mismatch and does it randomly. And so there's something called fibromuridine that incorporates as a T during DNA replication. But that is exactly as a T, except that because of the bromine atom, the tautomer is a lot more frequent. And so bromouridine incorporates as a T, but then will a lot more frequently than the normal base will pair with C. It forms the tautomer a lot more frequently, basically. And so it incorporates in front of A, and then during DNA replication, they pair with G and induce a transition. Okay, and that's actually a lot higher frequently than T. Is that clear? Is that okay? Any questions about that? So that was one example of a mutagen. And another example that's commonly, the mutagen that's commonly used is EMS, ethyl methylsulfonate. And that modifies G to form a modified base called O6-ethylguanine, which will steal some electrons here away from the oxygen and lead to a modified G that pairs with T instead of paired with C. So it does 2 hydrogen bonds and it pairs with T. And that's the way you write that. It's wrong in the book. And again, you're generating a transition mutation, a GC to an AT. UV can induce mutations. It cross-links adjacent T bases in the DNA. It generates thymidine dimers in 2 different ways shown here. That doesn't really matter exactly how this happens, but these are covalently linked T bases on the DNA. This cannot be replicated. There's a DNA repair mechanism for this. We'll discuss that shortly. This DNA repair system specifically for T dimers is active in plants and in very few metazoans. It's mostly a plant thing. In mammals, this kind of thing is dealt with by a system called nucleotide excision repair, which I've mentioned in a few minutes. Just a quick note, there's actually a test called the Ames test, which in fact quantifies the mutagenicity of certain compounds. So this is actually a test that's been developed something like 30 years ago, or maybe even longer than that, and is now commonly used in industry to quantify the impact that a compound, especially if something that's not been evaluated so far, has on the DNA, and does it induce mutation rates? And if it does, it's possibly a carcinogenic compound, so we have to be careful. So in fact, this is something the FDA uses as one of the reference points for compounds before they're put on the market, whatever they may be. This is actually using the reversion rate when, in fact, salmonella is placed in company of that compound. If you have put it on a plate, then you put the compound on the filter, and it's a His minus strain, and you look at the number of His plus reverters. And the funny thing is they have different strains. Some have frameshift mutations, and some, I think there's another strain that has missense mutation, so you can actually look at these compounds reverting different types of mutations, which is important to do. It may be something has an impact on frameshift mutations. It uses mutation in a different way, and you wouldn't see it if you wouldn't use different strains with different mutation types. This is something that's done in the presence of a mouse liver extract to make sure that the liver doesn't transform this compound in some way and generates in vivo a toxic product. So this is called the Ames test. Now I want to talk about, we've talked about how mutations arise. I want to talk about how these are repaired. So here's a little bit of a study sheet for that. There are a number of pathways. I already mentioned the mismatch repair. The DNA mismatches are dealt with by a specific machinery called this DNA mismatch repair. That's actually mostly active in S phase during DNA replication. Bulky adducts modified base at pyridinic site is dealt with by a machinery called the base excision repair. UV T dimers, that's photoactive repairs, not in mammals, I said that before, or the UVR ABC system in prokaryotes, that's called the nucleotide excision repair in mammals. So that's a highly conserved system in evolution. Also true for DNA mismatch repair. Double-stranded breaks are dealt in 2 different ways. they can actually be religated by a system called the non-homologous end joining system, or NHEJ, or they can be fixed by recombination or something that is related to recombination called synthesis-dependent strand annealing, or SDSA. We'll look at that in a minute. And importantly, there are signaling systems that detect the damage and activate the appropriate DNA repair systems. So to have DNA repair system is one thing, but you need to have a system that detects the damage in the first place and that activates that DNA repair system. And there again, there are many signaling molecules involved depending on the damage. So we're going to look at one particular type, very important, is the P53 system that senses DNA damage, leads to a pause in G1, allows for repair to occur, and if the DNA damage is too extensive and cannot be fully repaired, induces apoptosis, programmed cell death in these cells. So it's a very important tumor suppressive system here that is induced by DNA damage. And this is just one signaling pathway out of many. So this is a summary of the mismatch repair in E. coli. Active in S phase, highly conserved in evolution, and what I'm not going to ask you about these gene products and proteins. Essentially, how it works is the DNA is the mismatch is detected by a protein called a complex called MUTS and MUT-L that recruits another molecule called MUT-H, which will perform a nick in the strand that's damaged, recruit an exonuclease, and in fact digest that strand, and that allows for the polymerase. And this can occur in the leading or lagging strand, slightly different modalities, but that can be re-replicated and religated in DNA replication. You'll note that in bacteria, something interesting in prokaryotic systems in bacteria, it turns out the newly made strand is not yet methylated. And so it is the strand that's unmethylated, that is the newly made strand, that is actually degraded and resynthesized. And at the end of that round of DNA replication, then the newly made strand is then methylated. Okay, so in E. coli, the mismatch repair system actually will replace specifically the newly made strand because it can recognize it as the unmethylated one. That's fixing T dimers in the DNA. You have to just remember this happens in lower eukaryotes and plants, not in mammals. But there is a way to fix that in mammals. It's not the same one. There's an enzyme called photolyase that can resolve the dimers, and it's activated by visible light. So this actually is the dimer is actually a product of irradiation with UV light. It can be fixed by photolyase and activated by visible light. And this is actually an efficient and accurate way to repair this damage. In mammals, what you get here is a system that recognizes the damage and that will perform a nick on the damaged strand, something like 30 nucleotides downstream or 30 nucleotides upstream, and this whole strand will be excised. So you get a gap and it will be synthesized. So, and that's called it is called nucleotide excision repair system. And this is actually a evolutionary descendant of this system here that occurs in E. coli, the UVR-ABC system. So this is how this works. So in E. coli, you have a set of proteins that are recruited UVR-AD. There's a formation of the clot of the damaged strand, which would be the blue strand in this case. and a movement of UVRBC upstream of the damage, another nick that's made, the whole strand is excised, and DNA polymerase will fill the gap, and ligase will come in. So again, I'm not going to ask you a specific of these pathways, and the reason is because I'm going to ask you to remember other things today, so not this. So here's one thing I'm going to ask you to remember. It's the non-homologous enjoining system. And this is something that repairs double-strand breaks. So double-strand breaks, so here's what you need to remember though. Double-strand breaks have 3 ways to fix that. The non-homologous enjoining system, the synthesis-dependent strand annealing system, and recombination. Those are the 3. The last 2 are intimately related. So you won't have to remember 3 completely different things. NHEJ is what happens when there is no template to fix the double-strand break. Example, in G1, before DNA, if the DNA has not been replicated, and you break a chromosome, this happens with ionizing radiation, X-rays, for example, or X-rays, radioactivity or X-rays. And let's say the cell's in G1, and there is no sister chromatid. So the NHEJ can actually fix that. There is the break, as shown here, is actually recognized by a dimer called Ku. I don't know what Ku stands for. Does anybody know? But there's a dimer, and it has 2 subunits, Ku70 and Ku80. And this is a dimer that recognizes a broken DNA end. So if you have a duplex that's like this floating around, Ku70, Ku80 will recognize that. And will recruit an enzyme called DNA-PK-CS. CS stands for catalytic subunit. This is a huge protein, which is a kinase. And a kinase has substrates, and DNA-PK will phosphorylate substrates, which are currently not well characterized. But DNA-PK will orchestrate the repair and lead to the religation of the 2 broken DNA molecules. And no matter what their origin is, it may be the same chromosome, it can be a DNA chromosome. That's how translocation can occur. If you have 2 breaks in the same cell, the NHEJ doesn't know which end comes with which. It just religates 2 DNA molecules. The ligase that's involved is called DNA ligase 4. It's a dedicated ligase for this system. It doesn't work in DNA replication, so that has nothing to do with the ligase performing ligation in DNA replication. Okay, that's a repair ligase in NHEJ DNA ligase 4. So I want you to remember Ku dimer 70 and 80, DNA-PK, and ligase 4. The system, it goes along with active, in fact, additions and subtractions of nucleotides at the end. Ku actually chews a little bit, and there's additions of a few nucleotides. And when you've seen the religated product, very often you see not the actual sequence as it was before the break. You see the sequence is religated, but it has added and deleted nucleotides. There's some randomness to it. It's not always the same nucleotides, same number of nucleotides. So this is a repair that's actually error prone. If it occurs, if the break occurs within a coding sequence, the NHEGA will fix the repair, but usually will induce a correction. It's error prone repair. So dose and break, I told you that. Remember these elements. And now that we've done NHEGA, what else can happen is that in fact, the break can occur after DNA replication. So this is something that can be repaired using the sister chromatid as a template strand. So what happens there is that, and this occurs in S, so in G2, mostly in G2. And the break actually is resected on both strands. And the end that's actually resected is the 5' end. So you see the 5' end here is resected by an exonuclease, and the 5' end on the other strand is resected. And so you're getting 3' overhangs created after this resection. And there's a protein called RAT51, which is able to promote strand invasion from the overhang, the 3' overhang here, into the sister chromatid. After all, they're complementary, they're the same sequence. So you get strand invasion catalyzed by RAT51. So you remember RAT51, that's ultra important. And then you see there's a 3' end here that can be extended by DNA polymerase using the sister chromatid as a template. And this extension can actually go past the point of the break. And therefore, this strand has been resynthesized, can re-anneal with the other overhang that was created on the other end of the broken strand. And you need a little bit of gap filling here, but by and large, you've recreated the original sequence using the sister chromatid as a template. And here, there is no room for error. This recreates the original sequence. It fixes the break to the nucleotide. This is a perfect repair. Okay, this is not something that will generate errors as NHEGA does. And so that was the second mode of DNA repair on how to fix